Okay. All right. So we're going to continue now. Okay. Just to reiterate the question that was in the break regarding the syllabus and the books and everything, I'll put it up on the Moodle website. So you'll have the books that we will use. So for example, for Intro to Quantum Information, we'll be using the Nielsen and Chuang book. And for the Intro to Quantum Optics, we'll be using a little bit of the Serge Haroche Exploring the Quantum book. So I'll give those, I'll write those up on the website. Okay. But what I want to do now, I think I gave, pretty big introduction as to what's the purpose of this course and what are the technologies that we're going to be talking about. What I want to do now is let's specify them. Okay, so let's talk about the technologies themselves and what are we talking about. Okay. Now, there are many quantum technologies. For example, there's atoms, okay? And atoms, they will have neutral atoms, okay? Ions, okay? There's cavity QED. That's all those Rydberg atoms, what I was talking about when you send them through a cavity, and so on. There's photons, or optics. Photons, or optics. Okay, where you have manipulations of single photons, for example, or continuous variable states. Like cat states, GKP states, and things like that, if that says anything to anyone. There's NMR, one of the oldest technologies. Okay. Quantum dots, for example. Quantum dots. Okay. And in quantum dots, there's several types. There's ones like indium arsenide on a substrate, or there's ones where you have a substrate and you create some kind of confinement, so a 2D gas where you create in confinement and you have a quantum dot. There's those kinds of defects or implants. That's, for example, when you take some, again, silicon substrate or a highly purified silicon substrate and you implant it, for example, maybe with bismuth atoms or silicon carbide or phosphorus implants. Those are the three that I have written down. And there's also defects, NV centers. Maybe I'll write them down. So there's NV centers. So NV centers is defects in diamonds, basically. There's color centers, all kinds of other color centers. For example, in silicon carbide, this is in diamond. Okay. Bismuth implants in silicon. Okay. And at the bottom here, maybe I'll add just, okay, so these are the defects in implants. And lastly, I'll write here, superconducting circuits. Okay. Or sometimes more professional language is called circuit QED. Circuit QED. Okay. And all these technologies, okay, all these things, you can say that they have, they're trying to create some applications. And I would divide these applications into three main categories. And that would be computing, okay, Communications, and sensing, or metrology, similar things. Metrology. Okay. Now in computing, you would put also gate-based. There's also measurement-based quantum computing. You can also put here quantum annealing. Okay. Of course, simulations. So all these things I would say are subjects within computing. Okay. Communication. This usually refers to the ability to send information, quantum information, from one node to the other. And typically it refers to sending from A to B in a secure way. Okay, so we'll see, for example, we might talk about this a little bit, but it's basically the ability, that you can send information, qubit, from one place to the other, and if someone is eavesdropping, this can be detected with 100% ability. And the systems and this is used, for example, already for quantum key distribution, QKD, and things like that. So QKD, quantum key distribution, and things like that. Now, this whole communication aspect, okay, of QKD, this is basically almost commercial. Okay, you can go buy today systems that will send information from A to B in a completely secure way.
Shay?
Yeah?
It's hard to read the little, your writing.
Okay, write bigger. Okay, so which is this font size okay?
Yes.
Yes, okay, so this font size is bad. Okay, all right, noted. Will not write smaller than that. Okay, noted. But basically what I wrote here is, maybe I'll lower that, rewrite it. But, gate-based, okay, measurement-based, quantum computing. What else did I have? Put annealing and simulation, right? Okay, there. Okay, so I was talking about that. Communication in the sense of, quantum key distribution and sending secure information from one point to the other, that's almost commercial nowadays. Okay, you can go buy this and set up your little secure link. Sensing and metrology, that is very interesting. That's been going on for many, many years. These things like squids, sensing of, atomic clocks, and things like that. So those things are fairly developed. So these two things are fairly developed. I would say that computing today is really the forefront and what has brought in the last few years everything forward. Okay. Yep. And what we're going to do in this course. So I wrote here loads and loads and loads and loads and loads of technologies. Okay. And also wrote here kind of like the applications, so computing, communication, and sensing. Okay, and on the intersection of each and every one of these and these, you can say something and talk a lot about and learn a lot about. But what we're going to do in this course, we can't cover this whole phase space, this whole intersection between the technologies and the applications. So we're going to be focusing more on this side of the board, meaning more on the computing side, less communication and sensing. We'll mention these things, but this will be the most of the focus. Okay, and the technologies that we'll be focusing on most are going to be NMR, superconducting circuits, trapped ions, okay? We're also going to talk about some neutral atoms. That will be our guest lectures, okay? But basically, we're going to be talking about mainly atoms, superconducting qubits, and NMR, okay? Now, at this point, you might ask yourself, why did I make this choice? And the first thing, so the focus on computing, I kind of alluded to that, is that quantum computing is really the application, okay? This is the application. Like I said, communication in terms of secure communication is relatively well established, okay? Sensing is very diverse. There's a lot to do there, but it's been going on for decades. And really the big hype, and the reason that this is going strongly into academia and coming out from academia also into industry, is the computing application. It is the possibility to do information processing in a different way than what you're used to, okay? Not the regular computing sense, but now to use the abstract thing which is called a qubit, or a lot of qubits to do information processing rather than the classical bits, okay? So computing is the application. And this is what brought out the big hype. And this is why the focus is going to be more on this side. Second thing is NMR. Okay, so why NMR? And the reason is that NMR is a relatively old technology. It's relatively older, it's relatively established. It will never yield quantum computing. It is completely unscalable. Unless someone thinks of something crazy, but we will understand why it's unscalable. But because it is so established and known for so many years, it has also developed the language, okay? And the language that is used in many of these fields has roots in NMR, okay? So NMR is a very good spot to start off. It's a comfortable starting point to learn the subject and the language and get familiar with many things. So this is why we're going to be doing NMR. And why superconducting qubits and trapped ions? Basically because right now these are the two leading technologies for realizing quantum computing. I would say that there are two or maybe three more possible dark horses in these technologies for quantum computing, which is our now photons and neutral atoms, okay? And maybe quantum dots, I don't know. But this is kind of like why I made these choices and why I made the focuses for this course, okay? So this is what we're going to be focusing on in the course. Okay. Are there any questions till now? Okay. All right. This is a nice, easy lecture to start off with. Okay. I hope you don't get, so we're gonna dip into things soon. Okay. But I really want everyone to kind of like get a broad perspective and a broad understanding of what we're gonna do here, where we're heading, where we're starting, and where we're heading off to. Okay. And okay, so we understand the technologies here, and we understand the applications, and we understand what we're going to be focusing on in this course. And what I want to discuss now is, okay, so now you choose some hardware, okay, and you want to choose some application, and you want to go ahead with it and develop this into a technology. And what I want to discuss briefly now is what is the goal of this quantum hardware, specifically maybe with focus on computing, okay? So I'm going to focus on the question of what do we require from certain hardware, okay? So what is the goal? So what is the goal of specific quantum hardware? Okay? And the goal of a quantum hardware, you can state it in a very simple sentence, is basically to bring those quantum information concepts, basic quantum concepts, into reality. Okay? So the main goal is concepts need to come to reality. Okay? This is the main goal. You choose something, it needs to be able to do that. Okay? And the key challenges for any technology, okay, are basically, one, you need to have control over the individual constituents. Okay. You need to be able to couple them, because at the end, a single degree of freedom is not enough. It's nice for fundamental things, but now once you have single control over your little mini system, you need to start adding more and more. Okay, so you need to be able to couple them. Okay, so you need to be able to couple. And of course, you need to be able to communicate and measure that system. So we can call it readout. Okay. And also maybe you want to add here transmit. Transmit. So, send the information from one node to another node, and so on and so on. And you want to do it, someone asked before about the precision in the previous class. And I would say that you really want to do this with precision that will give you a technological viability. Okay? So we're looking at all these, and we're looking all this to give us some technological viability. Okay? If we're talking about computing here, then we're talking about, the coherence times of these qubits need to be enough. The fidelity of your operations needs to be enough. The speed of your operation needs to be enough. You need to be able to scale it. Okay? And these are big challenges. Okay? And what we want to do in this course, as we're looking through these technologies, and as we understand the basic concepts, what we want in this course is for all these technologies, we want to understand these things, okay? We want to understand for each technology, what are the challenges, what are the problems, how does it compare to other technologies? The tools that you want to leave this course with is the ability to open recent papers, recent research about atoms, about superconducting circuits, about trapped ions, about photons, and be able to infer, okay, what did the people in this experiment do? What did this developmental stage do? What are the new things that were discovered? Is it important? Is it not? How does this relate to all these things? This is what this course is about. It's about giving you the tools to understand and handle all these cutting-edge research happenings, basically. Okay? So this is kind of what we want, okay, from these technologies. And I want you at the end of the semester to leave with these abilities. Okay? Yeah. So maybe it's a little bit of reiteration, but we'll just repeat this, that the quantum information part that we talked about, so we're going to be doing quantum information, and the quantum information theory gives us a framework, okay? For example, it gives us the Hilbert space, okay? So we have our Hilbert space, and that's the framework that the quantum information gives us. But it really tells us nothing about how to realize that, okay? In this first lesson, we're going to see, or maybe the beginning of next lesson, we're going to talk about, what is a qubit, what are few qubits, and so on, and all the basics of quantum information. But those are abstract things, okay? What the technology does and what each platform does is it realizes that space. Okay, so the basic concepts are the quantum information, but each technology realizes and does these things in a different way. Okay, so each platform, okay, is a way of realizing everything. And the way I kind of think about this world of quantum information, maybe if I do some drawing here on this board, on the second board, is through interaction. And this is really why we're going to learn in the second part Introduction to Quantum Optics. Because the first part I said we're going to be doing Introduction to Quantum Information. And that's just to remind you of the concepts. That's to remind you of the concepts of quantum. But the quantum optics will give us the tools to understand how these concepts are realized with each technology. Okay? So the physical basis is really quantum optics. Or I think this is better than describing it as quantum optics, QED, quantum electrodynamics, but again, low energy quantum electrodynamics. Okay? Or if you want, light matter interaction. Okay? And the way I like to think about this world of low energy QED or quantum optics is in the following way. So we have basically, in this world, we have our atoms. Okay? And an atom you would describe with, let's say, some potential and some energy levels. So here's our drawing for an atom. Okay? And you may have a collection of atoms, like this. This is equally spaced, so maybe we'll have it like that. There we go. So you'll have a collection of atoms. And so atoms don't have to be real atoms. They can also be artificial atoms. So superconducting qubits or quantum dots or even defects can be considered artificial atoms. Okay? And on the other side we have light. Okay? Now light is basically, as you know or may not know, anyone knows the answer? Shout it out. What does this stand for?
Harmonic oscillator.
Harmonic oscillator, that's right. Light is basically a harmonic oscillator. There we go. Okay, so equally spaced levels. So we have an ensemble of harmonic oscillators. Okay? And most of these technologies that we're talking about, basically maybe all of them even, you can put in this framework of nonlinear oscillators, which are atoms, basically. Maybe it's a two-level system or a few-level system, but this is some form of nonlinear oscillator. And a linear oscillator, that's a harmonic oscillator, and some interaction between them. Okay. And these can also interact with the environment. So we'll put the environment down here. Okay, or sometimes we like to call this a bath. Okay, environment or a bath. And the environment or a bath is also what? How do we model this? Anyone? No? No one? The environment is also going to be a collection of harmonic oscillators. Okay, and we're going to have some interaction with this, and the environment in general is going to be causing, dissipation, things like that, but the environment is also us. Okay, so we want to measure a system, we're also the environment. So we need some form of interaction. So you have your nonlinear oscillators or atoms, they're interacting with light harmonic oscillators within this paradigm, but there's also us in the environment, and we need to be able to communicate with all of these. Okay, and this is kind of like the way I see it and the way I see these quantum technologies. It's basically some interaction of nonlinear oscillators with linear oscillators and a little bit of environment. Okay? Any questions till now? We okay? All right. Okay. So, as you know, in real systems, we also have noise. Maybe I'll move back to this board over here. In real,
Shay?
yes?
The recording is on.
The recording, what do you mean? Is the recording on? Your faces are not recorded, but the lesson is recorded. Okay. So in real systems, we have noise. Okay, and we're talking about technologies and real hardware and real things. And while you can go ahead and teach a quantum information course and ignore noise completely, you can't really talk about quantum technologies without even mentioning noise or realizing it's there, because it's a big part of it. Okay, so real systems will have noise. Okay, so real systems have noise. Okay. And in all quantum technologies, whenever you're talking about a quantum technology, when you're thinking, okay, how am I going to build something with this, some information processing, then the noise in the system has to be considered. Okay, and you need to be able to know how you're going to deal with this noise. And in the most advanced case, if you're thinking of building a quantum processor, you need to be thinking about something called error correction. Okay. Now we're not going to be talking about these advanced subjects here. You need to learn them first on the theory level, and if someone's interested in that, and I really recommend to learn about quantum and error correction codes and things like that, it will be talked about in the advanced quantum information course that's given by Itai Arad. Okay, so noise and error correction on the theory level is going to be given here. Okay, but we're going to just keep it in mind, these things. Okay, because this noise thing is important. Okay. And it's something that when you're talking about a technology, you have to be aware of. Okay? So hardware development, okay, is always aware of noise. Okay? Or even more strongly, is always aware of error correction. At what level do you need error correction? What are the error correction codes that you will need? And so on and so on. Okay? Okay, so this was very kind of general statements about the technologies. And what I want to quote to you here, if we're deeping, a little bit closer into quantum computing, and in about a few minutes we'll be done with this introduction, but I really want to finish off this introduction with quoting what is called the DiVincenzo criteria for quantum information processing, or for quantum computing. And these criteria, okay, this is a 2001 paper, by the way. Okay, and these criteria give us basically the physical requirements. Okay, maybe I'll write it down. These are basically the physical requirements. Okay. So under consideration of noise, that we're talking about real systems, what are the physical requirements of a system? And the first thing on this list is scalability. We already had that on a different list. Okay. So we want this system to be scalable with well characterized qubits. Okay? Now remember, your physical system doesn't actually have to be a qubit. It can be a few level system, but at the end, something you pick out to be a qubit. Okay? And the second thing is you must be able to initialize the qubit. So ability to initialize the qubit. Okay, whatever is representing that qubit, your atom, your circuit, or whatever. The third thing, and this is with regards to the noise, okay, you must have high coherence times. Okay. Specifically, they need to be much larger, right, than your operation time. Okay? So basically, you need to be able to do many operations within a coherence time. I would add that this may not be sufficient because maybe I have coherence times of a year, but if it takes me an operation, if a single operation takes me a few days, and I have some algorithm that takes, I don't know, 10,000 operations, then waiting for a few days times 10,000 really makes it impractical. Okay? So I would say that the operation time itself also has to be, small on a human scale. Okay? But I don't think that's a big issue. But just to mention that thing.
Don't we have to compare it with the error correction time rather than the operation time?
Well, okay. So this is very general. And if you're thinking about some error correction in the future, then I don't know if you know or not, but every error correction code at the end has some threshold. Okay, it means that if it means that if the error, your gate error, readout error, all your errors are below this threshold, then you can always add more and more and more qubits to create a redundant encoding such that you will increase your effective coherence times. Okay, this is the big thing about error correction. If your hardware is above that, putting more and more and more qubits will just make it worse. Okay, so you have to have coherence time that is much longer than the operation time, and for error correction, you need it to be below a certain threshold. This I have it. Let me finish this list. I have it on the last two things of the list. But I'll write it down on the board in a second. There was another question?
Yeah, how exactly do you define the coherence time?
Oh, okay. We're going to be discussing that. Remember, now this is like a big, big fluff intro lesson. Okay, so there are terms here that I might have said that I'm sure not all of you know about or familiar. I've not defined anything. We're in a few minutes going to be defining, like from zero we're starting. I'm going to define what is a qubit on the board. I'm going to define what is entanglement. I'm going to define all those things. Then we're going to define spins, light, all those things throughout the course. Okay? So,
great.
But ask questions if you need. Okay? So we must have high coherence times. Okay? And 4, we need a universal gate set. Okay, universal gate set means that we should be able to do any logical operation. The typical simplest universal gate set is full control over a single qubit and some 2-qubit gate. Okay, number 5 on the DiVincenzo list is measurement. You need to be able to measure your qubit. So qubit measurement. Okay. So this is qubit measurement. And 2 more things on his list. which might not be directly to a quantum processor, but if you want to link them up in a network, and when I talked about communications, I talked about QKD, but now we're talking about, you want to link up two processors in a node, so you may call that communication also. But, for a network, in addition to all these things, you need to be able to convert stationary qubits or stationary states to flying states. Now these can be flying in free space, or they can be in the fiber optic or whatever. And you need to be able to faithfully transmit them. Okay, so you need to be able to take your qubit, for example, all right, send it out, and you need to be able to catch it at the other side. Okay, so that's what we mean by faithfully transmit. Okay, with regards to what was asked before, so up to here, this is the famous DiVincenzo criteria. Okay, for a quantum processor. And this is my addition to it, okay? So I would like to add this, add two criteria, okay? So we'll do this with A and B. So A, it must be compatible with error correction code. Okay, now an error correction code is just how you encode a single qubit in multiple qubits. And when you build your hardware, you need to be aware of this, and it needs to be compatible with this. Okay, and it's basically due to the fact that you will never have enough coherence. Okay, suppose that you have coherence to do a computation of 1 minute, your application will need 2 minutes. Okay, and you need to be able to scale your processor, scale your quantum information processing unit in a way that doesn't require you to, improve the materials, improve the basic constituents, because that is hard research that can take years. You don't want to rely on that. But if you do have an error correction code, okay, with some threshold, and you pass that threshold, then you can do that. And so you must be compatible with some error correction code in order for this technology to really be viable for some future quantum processor. And B, to actually realize it, your technology must at the end have, error rate lower than the threshold. Lower than threshold. Threshold. Okay? Now I'm writing this, I think these are two more recently modern opinions. This is my own personal opinions. But I think this is important to mention. And I think what is more important to mention in our context is that no technology has fulfilled B. Or maybe B plus 1. Okay? So this thing, B, must have error rate lower than threshold, and number one that we had on the other board, scalable, with well-characterized qubits. No technology has demonstrated this till now. Okay? And when some technology demonstrates that, meaning being scalable, having the ability to add more and more and more and more and more qubits, but still be with an error rate lower than the threshold, that's the point where we will actually have real quantum computers, real useful quantum information processors. Okay? That's it. Now, I want to make a final note. I had a couple of questions in the email asking me about quantum supremacy. This is an experiment that was carried out about a year ago by the group in Google, Supremacy Qubit. So basically, they claim that they did on their quantum processor some calculation within 3 minutes that would take the most powerful computer in the world 10,000 years. IBM later claimed that they can do it in 2 days. And some people claim that there's something wrong with the experiment. It was done over more than a year ago, so it's summer of 2019. But if you want to read up on that, here's a nice blog by Scott. I'll write it down. I'll give you the link. I'll write it on the board. This is a fun discussion and a nice explanation by Scott Aronson. Scott Aronson is a computer scientist. He's very famous in the field of quantum computing, and he has a great blog. He's a great communicator, and he explains things nicely. So for those who asked about the quantum supremacy and want to knowledge details a little bit about what went on there, so I'll write the website of his blog. So it's basically scottaronson.com/blog/P equals 4372. Now this discussion is almost a year old, but it's very enlightening and it's fun, and there's a lot of nice discussions and things that he writes up about quantum computing. So it's I would say it's recommended. Okay, not only for those who asked me about it. Okay, now we basically have 5 more minutes. Are there any questions now about? So I'm done with the introduction. Okay, so if there are any more questions about the introduction, what's going to go up in this course, what we're going to be doing, now is the time to ask. If not, I'll just present what is a qubit and start reviewing quantum information in the 5 minutes that we have left. No? Okay, all right. So let me just, in the 5 minutes, do what is a qubit. Maybe I'll ask you a question and you can, on the yes/no thing, answer for me. That would be nice. How helpful was this discussion? Was this intro? Did it sort things out for you, or are you ending up with more question marks about what we're going to be doing in this course? A yes answer means this was great, it sorted things out. A no would be like, I have no idea what you're talking about. All right, I see yeses, loads of yeses. There is one no. Okay, all right. If we only have one no, then we're in a good situation. The one no can always ask questions, by the way. And you can also come to me and ask and send emails and so on and so on. Okay, so I'll just recap again. The course, we're going to start with some intro to quantum information, quantum optics. That will build up the basis to talk about the quantum technologies themselves. Okay, all right, great. So what I'm going to be following. Okay, so we're talking about quantum information. I'm going to be following the book Quantum Computing and Quantum Information. Quantum computing, quantum information intro by Nielsen and Chuang. Okay. Okay, so what is a qubit? I assume that you've all seen this at some point. Okay, but basically qubit is a two-level system. Okay, it is isomorphic to basically a spin half. Spin half. Okay, you've all seen a spin half. You've solved it several times. So that is a qubit. And the wave function of a qubit is just written like this, usually in some basis. So you choose a basis. You call your two states 0 and 1. And then your wave function is just some alpha 0 plus beta 1, where alpha and beta are complex numbers. And of course, we have normalization, which means that alpha squared plus beta squared equals, anyone, just to show me that you're listening? 1. Thank you. All right, great, excellent, fantastic. All right. And you also know that this can be represented on a block sphere. So a block sphere. By the way, please mark no if this is the first time you're seeing this. I want to know if there's anyone like who has never seen this. Okay. So this is the block sphere. Okay. And the block sphere is basically, this is supposed to be a sphere. Maybe I'm not that good at drawing a sphere. Okay. So this is x, y, and z of the sphere. Okay. And basically it's parametrizing alpha and beta. Okay. So we call this state over here 0. We call this state over here 1, and then our wave function psi, okay, if we parameterize alpha and beta, it can be written as cosine theta. I'll draw theta and phi here in just a second. 0 plus sine theta e to the I phi 1, okay? And if I draw a vector here, so this is on the face of the sphere. So we have the block sphere, and we're representing this state on the sphere. And this angle over here is theta. And if I draw this like that, and then the angle from the x-axis, this will be phi, but I have, this is minus phi. So it doesn't matter. This is the angle phi. So this is cosine theta, and this is sine theta, e to the I phi, and this is basically a qubit. So this state here represented on the sphere, this is psi. Okay? All right, great. Now, with regards to a qubit, one of the first things that we're told after being introduced to a qubit is that a measurement, okay, okay, will yield a specific outcome. Okay, it will either yield 0, and the probability for 0 is alpha squared, or it will yield 1, and the probability of 1 is beta squared. Okay, and the implicit assumption is that this measurement is actually a projection. Okay, so maybe measurement is the wrong word. Okay, we're talking about a projection. So when you project the system, you will get either 0 or 1, and these will be the probabilities. Okay, and I think I have to stop now. So we will continue from this point next week. Okay, if anyone has questions, you can ask now or just log out.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Thank you.
Yes?
Shay, could you move a little so I can see what
Oh,
you
sorry. Yeah.
wrote?
Go ahead.
Thank
Yeah. You can also copy this from Nielsen and Chuang. I think it's their drawing may be prettier than mine.
Shay?
Shay?
Was there another question?
Okay. Would you explain what is coherence time? That it's supposed to be much larger than the operation time.
Yeah. So coherence time, we're gonna be very specific and understand exactly what it means. But on the very high level, it's the time that it's the characteristic time where the qubit loses its coherence, and the coherence is basically there are two processes. One, your qubit can switch from 0 to 1. Okay, that's called a bit flip time. Okay, in real systems, if there's an energy splitting, then this would be higher energy than this, so there would be some relaxation in a preferred direction, and that's called like T1, for example, in NMR. And the other characteristic event that happens is a phase flip. So suppose that you flip from a superposition of 0 plus 1 to 0 minus 1. Okay? And that is typically called T2 in the NMR language. And those two times are called coherence times. It's basically a characteristic lifetime of the qubit. Okay? It's, the probability of it having an error, or the rate of error. 1 over those times is the rate of your error. Okay?
Great. And NMR is magnetic
nuclear
resonance?
magnetic resonance. Yeah, it's
Okay.
Yeah. Well, we're going to be doing that in detail. So it's basically a spin half manipulating and seeing what happens there. Yeah.
Great, thank you.
Any other question? All right. So I'm going to close the Zoom.
I had a question.
Yes.
I had
go
a
ahead.
question. When are the recordings are going to be available?
I don't know because I'm not recording this. The Zoom is not recorded. The board and the video is being recorded. Okay.
Yeah.
So there's some other system. It will be linked onto the website somehow. Okay.
Okay.
All right. But it will be available.
Thanks.
All right. Thank you.